Welcome to the Explainer. I am so incredibly excited to get into today's topic with you. We are looking at a concept that, quite frankly, is quietly running the entire modern digital world. We're talking about decoding the matrix. We're going to see exactly how mathematicians and computer scientists find these hidden, highly interpretable factors buried deep inside massive, otherwise incomprehensible datasets. Let's dive in.
Okay, let me ask you something to get us started. What does the math powering your absolute favorite movie recommendation have in common with, say, a compressed JPEG image sitting right there on your phone? I know, it sounds kind of like a trick question, tying human movie tastes to digital pixels. But the answer to both lies in a brilliant mathematical concept called matrix decomposition.
So here is our roadmap for today. 1. Decoding the matrix. 2. Determinants and eigenvectors. 3. Singular value decomposition. 4. The movie rating matrix. And 5. Compressing images with math. We're going to go from abstract algebra straight into the real-world tech you use every single day.
Section 1. Decoding the matrix.
The fundamental problem we face in machine learning, really in any data science, is that raw numerical data is often just way too large and complex to analyze directly. The solution? Matrix decomposition. Think about when you first learned to factor a massive, unwieldy number into a clean set of prime numbers. It's a lot like that. By describing a complex matrix using factors of smaller, interpretable matrices, we are essentially revealing the core DNA, the structural building blocks of the data itself.
Section 2. Determinants and eigenvectors.
To actually break down these matrices, we need specific tools. Let's start with eigendecomposition, which means we need to understand what an eigenvector actually is. By definition, an eigenvector is a vector that, when you apply a linear transformation to it, changes only by a scalar factor, which we call the eigenvalue. The key here? It retains its exact original direction. You can really think of these as the crucial atomic building blocks of our mathematical analysis. They're showing us the primary axes along which our data is organized. You can actually visualize this physically right here. See that light blue circle of vectors being mapped into an elliptical shape? Notice how the eigenvectors, the specific red and blue arrows, stay pointing in the exact same direction even after the transformation. They're literally stretching or compressing the geometric space by a factor of their eigenvalue. So they're reshaping the data, but remaining fundamentally grounded in their orientation.
Now, to actually find these values, mathematicians historically used determinants. And while modern computers use much faster numerical methods to analyze these matrices and stabilize computations, determinants still remain an incredibly powerful theoretical concept. They really help us understand the overall orientation and the volume of our data space. Section 3. Singular Value Decomposition.
Okay, so here is the catch. We're pivoting to the true hero of this explainer, because that eigendecomposition we just talked about, it has a major limitation. It inherently only works on square matrices, where the rows perfectly match the columns. But let's be real, real-world data is almost never perfectly square, and that is exactly where singular value decomposition, or SVD, comes to the rescue. SVD works on all matrices, period, regardless of their dimensions.
Let's define this clearly. SVD is a factorization that extends spectral decomposition to any matrix. We write it as A equals U times sigma times V transpose. The legendary mathematician Gilbert Strang famously referred to SVD as the fundamental theorem of linear algebra. Why? Because it applies universally, and it flawlessly quantifies changes in the underlying geometry between vector spaces.
Take a look at what that equation actually means in physical space. It's practically a geometric dance. SVD literally takes a square grid of data, represented by those colored dots, and transforms it systematically. First, V transpose rotates the grid. Then, the sigma matrix stretches it by the singular values. Finally, the U matrix rotates it again into a totally new space. It's a highly structured sequential transformation.
So how do we actually compute this? It breaks down into a highly logical, three-step recipe. Step 1, we find the right singular vectors for our V matrix by calculating the eigenvectors of A transpose times A. Step 2, we find the singular values for our sigma matrix by taking the square roots of those eigenvalues. And step 3, we grab the left singular vectors for our U matrix using A times A transpose.
Seeing those exact steps play out on a simple 3x2 matrix really reveals the magic here. you can see how the math systematically extracts independent directional data, that's your U and V matrices, alongside the diagonal singular value matrix right in the middle. I know, it looks like a dense wall of numbers at first glance, but it's really just following that exact same three-step recipe to completely pull apart the matrix structure.
Section 4. The Movie Rating Matrix.
All right, let's step away from the abstract equations for a second and look at a real-world application, finding hidden structure in human behavior. Take a look at this movie rating matrix. We've got 3 columns for our users, Ali, Beatrix, and Chandra. And the 4 rows are movies, Star Wars, Blade Runner, Amelie, and Delicatessen. Inside the grid are their personal ratings from 0 to 5. Now, to a computer, this isn't pop culture. It is literally just a 4x3 matrix.
This is where it gets really cool. By running SVD on this exact grid, we uncover hidden preferences. SVD effortlessly captures rating relationships and discovers latent or hidden features. For instance, the math basically figures out on its own that Star Wars and Blade Runner share a latent sci-fi trait, and that Chandra has a high affinity for that specific trait. This matrix factorization is the absolute foundation for how algorithms predict what you're going to want to binge watch next.
Section 5. Compressing images with math.
For our grand finale, we are going to visually see SVD physically compress data right before our very eyes. Look at this beautiful, original, high-resolution image of Stonehenge. To us, it's history. To a computer, it's just a massive matrix. Specifically, 1,432 rows by 1,910 columns, entirely full of grayscale values mapped between 0 for black and 1 for white.
Let's dive into this comparison. Original image on the left. On the right, things look a little blocky, right? These are rank 1 and rank 2 SVD approximations. Thanks to a mathematical principle called the Eckart-Young theorem, we can truncate our SVD equation to just the top singular values. This vastly reduces the data we have to store, while the math is actively attempting to minimize the visual error.
But watch what happens as we move up through these progressively higher rank approximations. Rank 3, rank 4, rank 5. You can literally see each outer product layer systematically adding critical structural detail back into the Stonehenge image. The math is brilliant here. It prioritizes the most important structural shapes first, all based on those singular values.
Here is the absolute game changer, the raw computational power. Instead of storing n times m values for a whole image, which eats up tons of memory, SVD lets us store only n plus m times k values, where k is the rank we decide to truncate at. This simple algebraic reduction achieves massive data compression without completely losing the structural integrity of the file. Bringing it all together, Gilbert Strang hit the nail on the head when he called this the fundamental theorem of linear algebra. From recommending your next favorite film to intelligently shrinking your digital photos so you don't run out of phone storage, SVD and matrix decompositions truly are the silent, hidden engines of modern computing.
Which leaves me with this one final, slightly provocative thought for this explainer. If singular value decomposition can flawlessly extract the core DNA of our highly subjective movie tastes and easily compress our physical photographs, what other hidden dimensions of your digital footprint are currently being factored? Just something to think about the next time you leave a trail of data online. Thank you so much for exploring this with me today, and I'll see you next time.